So today we're going to be starting off by talking about some basic terminology for formal languages. Before I can talk about what a language is, I need to make sure that everybody's kind of speaking the same language when it comes to the different, well, there's that M word. What is it called? It's a mayonnaise? Mustard? Either way, it makes a good sandwich. We need to have some terminology to help us understand what we're going to be talking about here today. So the first place I'm going to start is with the concept of an alphabet. Now, I'm not talking about alphabet soup, although that can be pretty delicious, okay? But an alphabet is a finite non-empty. That just simply means that this has to be a collection of symbols. Empty set. So set is just a collection of symbols. So it can't have no symbols. That's all it means by saying it's non-empty. And it has to be finite, meaning that you can imagine it like I have a bucket. So I have a bucket, and inside of here, if I peer into this bucket, I can see all of the symbols that I can use. For example, I have a typewriter. I may have all the alphanumerical characters along with some punctuation. Those would be my alphabet, for example, for a typewriter. Maybe I would include, say, some arithmetic symbols in there too, but anyways. So often we use the symbol capital sigma, which I'll just colloquially refer to as sigma, just to keep things simple here, for alphabets. So if you ever see me write down the symbol sigma like that, and not in the context of adding things, but in the context of talking about strings, just assume I'm talking about some alphabet. So let's talk about some examples of alphabets. So for example, I could say that sigma consists of two symbols, 0 and 1. So what kind of set of symbols? Sorry, I'm getting really worked up about this. But if you could think of, if I were to type on a keyboard or type some symbols down and they're just zeros and ones, what would I refer to that as? Like, what are zeros and ones? What are those? So just to give you a heads up, for example, if I had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's decimal, right? But what's it when I just have 0 and 1? Starts with a B. Starts with a B. Binary, yeah. So this is actually what we'll refer to as the binary alphabet. So this is the binary alphabet. Very good, very good. See, chat's on this, okay? So I can also now keep in mind you don't have to use capital sigma to declare the alphabet. I could give it another name. For example, I could call it capital A. This, for example, could be the set of all lowercase letters in the English alphabet. See what I did there? So this could be the set of all lowercase letters, just as an example. There's another example. Let's think about another one. I could, for example, have it where, coming back to my example talking about, say, a typewriter, or you can think of it like a keyboard. You could have a valid set of characters or symbols that are used to write out a message. You could have it where sigma, for example, could just simply be the set of all ASCII characters. So that would be, for example, all the characters on your keyboard or symbols. So all of these are examples of alphabets. So the point is just it's some non-empty set of symbols. Just to be clear, actually I have a question for you. Just to reemphasize this definition, if I gave you a set that looked like this, there's nothing in here, otherwise written as this. This is what we would call the empty set. Is that an example of an alphabet? So is this an alphabet? So just to make sure we understand this definition, so it's a finite, non-empty set of symbols. Well, no, this isn't an alphabet, right? Because it's empty. These aren't. This is. Keep in mind, these are both the same thing, but most certainly they are not alphabets because they are empty sets. They don't have any symbols in them, right? The point is the alphabet has the symbols we can use to write out what we're going to refer to as strings. So, what's a string now? So now we're going to build up to a string. So, what's a string? It's, for our purposes, it is a finite sequence. And I must stress that you can define strings to be an infinite length, okay? So, just for now, we're just going to think about a string as a finite entity. A finite sequence of symbols from some alphabet. Right, that's not too scary or anything, and quite intuitive. You can imagine I have my bucket of characters or symbols I'm allowed to use, and what I do is I pick out those and I can almost look at them like stamps I can put down and press on a piece of paper. And whatever I get out of that alphabet is a string. So, for example, if I wanted to have, let's just do an example. So, for example, 110010 is a binary string. Why would I call it that? It's because it uses symbols from the binary alphabet, right? So that's an example of a string. This is just one using the binary alphabet. Likewise, I can also have another one. I can, for example, write down kitty cat. So kitty cat. So this is a string, right? And it's using the alphabet A. It also technically could use the final example alphabet as well, like this one here too as well. So are there any questions so far? I think this is pretty straightforward, right? You can imagine I want to write out a string. A string is just a sequence of symbols, and they're just from some alphabet. So you have an alphabet, and then from that alphabet you can construct strings. So as long as we understand what an alphabet is and a string is, we're doing pretty good. Is everybody good with that? I think we're doing okay. Make sure you show some love in the chat. So, happy. Welcome on in. So, now that I've defined what a string is, remember it's a finite sequence of symbols. So that means that I can go over to a string and I can count the number of symbols it has, right? So that allows me to define something that we're going to refer to its length. So the length of a string, X is the number of symbols in X. Which we will denote as follows. So whenever I want to get the length of a string, I'll just write it with vertical bars on each side like this. You might be familiar with this. If you're familiar with a little bit about set theory, you might be familiar with that be indicating size or cardinality. So the same translates over here. So let's do some examples. I think that's a pretty natural place for us to go. So as an example, suppose I give you a string that just has 0. So there's one symbol, right? This is a binary string. It just consists of a 0. What's the length of this string? Can somebody tell me what the length of the string is? What's the length of that string? And I must stress that these are vertical bars. They're not ones here. It would be 3 if these were ones, it would be 3, but right now I just want to talk about this one. 1, yes, it's 1. I should be clear, and I should be very careful when I use this notation. And a piece of advice I would give you is if you use this notation, make sure the bars are a bit taller, kind of like I drew right here. But also, if it's unclear, maybe instead of writing it like this with a tick, maybe write it with a little bit more to the 1, just to make it a little less ambiguous, okay? So that's an example there. That's usually my opportunity to bring this up, is try to avoid being ambiguous, okay? So notice naturally I write a 1 like this. But the point is it's not confused with this notation. Let's do another example. So just following my advice now. So if I have 1, 1, 0, 0, 1, 0, what's the length of this string? Six. Yeah, see, 1, 2, 3, 4, 5, 6. See, you guys get this. It's very nice and simple. All you do is just count them. It's very intuitive. Just to really make sure we all understand this, let's check out what the length of the string kitty cat is. So all it is just how many symbols are in the string. And I must stress that we're talking about counting these. We're not talking about the number of distinct characters. That's a different concept, right? Because the number of distinct characters would be counting how many unique characters there are, as opposed to how many there are. So we care about how many there are. So what's the length of kitty cat here? And remember, there are no spaces or anything. Because remember, a space could technically be a symbol, at least if we're using ASCII. But remember, my example, I used the alphabet A. Yeah. Very nice, very nice. Now this is where it gets a little bit fun, because I've talked about having strings, and I said it's finite, right? But I didn't say anything about the possibility of a string that can have no symbols, which is technically possible. And this brings me to a concept called the empty string. So we have the empty string. So this is an interesting but important concept. It's simply a string with no symbols. It has 0 symbols. And we often denote it, and I must stress that different authors will use different conventions for denoting the empty string, but commonly you'll find that it is denoted as lowercase epsilon. So it's the Greek letter epsilon. So this is epsilon. And I must stress, we have to be very careful here, that epsilon, the empty string, is a very special symbol, because it isn't technically a symbol of any alphabet, right? It just represents the empty string. So the empty string, so string epsilon, is not a symbol, in an alphabet. So just please remember this. When somebody writes down as epsilon, it's not a part of any alphabet, because it represents a string with no characters, right? So please, if you're wondering what this would represent, and say if we're talking about, say, programming languages or anything like that, you may be familiar with it looking like this. Like where in a string you might denote it with double quotes. Say it has no symbols. That's an example of the empty string. So that's what epsilon is, if you're familiar with that concept. So just remember, It means there are no symbols in the string. It's not the same thing as me saying that it isn't, like, this is, it's denoted with a symbol, but it is in itself not a part of an alphabet, okay? So it's a little weird when you first think about it like that. Is that clear, everybody? Is that the empty string is just a string with no symbols. In programming languages like Java or C++ or languages that will use double quotes to denote a string, it'll just look like two quotes like that with nothing in it. But it's still nonetheless a string. Now, once we have strings, we can start talking about sets of strings. So we can describe sets of strings. So you notice that we're sort of building up to something here. That's not a coincidence, okay? So now I want to talk about a few bits more of notation and another concept about strings you might be familiar with if you've heard of strings before. So now that I've defined what a string is, we know what a string is, I want to talk about different ways we can have sets of strings. So I'm going to mention that and also an operation we might use on a string. So some common ones. So some common ones include the following. So each of these will have their own special symbols to talk about it. So we're going to first talk about the idea of powers of an alphabet. And I must stress that this concept easily generalizes. So I could talk about an alphabet raised to some power. So just like you have like a number and you raise it to an exponent, you could do the same thing to a set of strings. And namely, you could even do it to the alphabet itself. So what does that mean when I do this to the alphabet? It's going to be simply the set of all strings, of length k. Of length k, where all the symbols come from the alphabet, right? So let me give you some examples of what I mean by this. So if I gave you the binary alphabet, so remember the binary alphabet is just simply the set that contains two symbols, 0 and 1. So if I give you the binary alphabet, then I can write, then if I gave you sigma squared, so I'm squaring this right here, it says that this is the set of all strings of length 2 from the binary alphabet. So what you do is you just simply take the symbols and you write out all possible strings of length 2 using these two symbols. So for example, I can use 0 and I can use 0 again. There's a string. I can write 0, 1. I can write 1, 0. And I can write 1, 1, right? These are all strings of length 2 using these two symbols. So it can use all zeros, it can be all ones, it can be a mix between the two. So that's, for example, sigma squared. So yes, you can square the binary alphabet. So anyways, let's do another example. You might ask, okay, so what is sigma raised to the power of 0? So when you're staring at this, you're like, okay, sigma to the power of 0. Now, if we were talking about arithmetic, like numbers, very often you would just presume, oh, something to the power of 0 is 1, right? But remember, that's not necessarily how this definition works, right? It says the set of all strings of length, whatever that is. So what's going to be in this set? And I must stress that a set is just denoted here with these curly braces around the objects inside of it. So what we call the elements of that set. So what is this then? So what's going to be right in here? What's inside of here? So let's look at the definition. It says the set of all strings of length 0. I talked actually about this just a moment ago. What are all of the strings of length 0? How many of them are there? How many strings are there of length 0? How many of them exist? Close. It's not the empty set, it's the empty string. Empty string. So remember the empty string, that's epsilon, right? So that means that if you take any alphabet, you raise it to 0, it's actually just a set containing epsilon, the empty string. So, but the reason why I say that's a very good guess, because it's a very common mistake that people make when they start thinking about a set that contains the empty string. So I will clarify this. So note that this is empty set, which is a set that contains no strings, right? It has nothing in it. Has no strings. So the empty set is actually not equal to the set with the empty string in it. Why? Because the empty string is still a string, right? How many things are in here? 0. How many things are in here? 1. The empty string. Does that clarify that? So this is just some examples of using this notation, and I thought it would be a good opportunity to kind of distinguish the difference between a set containing the empty string versus the empty set. So another concept, and it's related to what we just defined here, is we call it often I'll call it often sigma star, but it actually has another name as well. In fact, it has a couple different names. So it's sometimes, so this operation is sometimes called Kleene Star or Kleene closure. I'll refer to it as Kleene Star. Now you might ask, what the heck is a Kleene? If you're wondering where that comes from, this is actually the name of a logician that actually did a number of, he developed a lot of the theory actually I'll be discussing at some point if I talk more about theory of computation. In fact, we'll encounter a theory of this logician's name, Stephen Cole Kleene's name. So this is the name of a logician. So by today's standards, a lot of the stuff that he was doing was what we would call today computer science. But a lot of pioneering computer science was logic. So, well, specifically mathematical logic. So, anyways, let's define what this is. So, I must stress that this is often written like this. So, you have the alphabet, and you raise it to a star. So, some will just abbreviate this as using a star operation on this set. So, instead of it being a number, it's just a star, okay? An asterisk. So, this is the set of all possible strings, the set of all possible strings, whose symbols come from sigma, the alphabet. So just to be clear, what that means is a way you could define sigma star is as follows. So sigma star is actually the same as me writing as follows. It is all the strings of length 0 using the symbols in the alphabet, combined with, so I'm going to use a union operation. It's just simply going to mean I'm going to dump all of these strings into one super bucket, which is a set too. So I'm going to lump these all together. So I'm going to take all the strings of length 0 that use the alphabet. I'm going to take that and combine it with the set of all strings using the alphabet of length 1. I'm going to combine this with the set of all strings of length 2 using the alphabet, and so on. So a question. Is sigma star a finite set or an infinite set? So you can clearly see that for some fixed number, so k, this is indeed going to be a finite set, right? But is this a finite set? Is sigma star a finite set? It's infinite, right? Because remember, it's all the ones of length 0, all the ones of length 1, all the ones of length 2, all the ones of length 3, all the ones of length 4, all the ones of length 5, all the ones of length 6, and so on and so on and so on, right? And remember, the alphabet is non-empty, meaning that there is at least one symbol in that alphabet, right? That set has at least one symbol in it. So it means that if you're considering all possible strings of a given length, it has to be some combination of the symbols in said alphabet. And that's at least one. So if I'm enumerating an infinite number of these, each one is going to have this, none of these are going to be empty, right? Excellent. As a remark, if we ever want to have the set of all possible strings over an alphabet, but I don't want the empty string. There's another piece of notation I want you to be aware of. Some people use this a little bit more often. It's sigma with a plus instead of an asterisk or star. So this is just simply, so this is the set of all strings like sigma star without epsilon. So it won't include this one right here. It will include all the strings of length 1 and up. So just as a remark, I just thought I would mention that. Okay. So that's so these are actually a couple of different sets of strings. Are there any questions about these, or is it pretty darn clear? I must stress that these concepts do easily generalize over other sets of strings. This is just over the alphabet. But I haven't yet talked really about general sets of strings yet. I just talked about over the alphabet. So if we're okay with this, let's proceed to talk about an operation that we can do with strings. This is another piece of the puzzle, okay? Okay. So now that we've talked about what an alphabet is, we talked about what a string is, I want to define, so I'll say, so it's important that we know how to multiply strings. So how do we multiply strings? In my earlier years, this concept was very fascinating to me. But you might know it under a different name. So you may know this as concatenation. So this is often referred to as concatenation. That's the fun word of the day. So this is where if you have two strings, if if you have two strings, one is appended, meaning that you attach it to the other one. One is appended to another. So let me be a bit more precise about what I mean by that, in particular more exact about this, okay? It's important that I do that. So just be a bit more precise. If I give you two strings x, and it's x1, x2, x3, and so on, and the last symbol is x sub k1, and y is equal to y1, y2, y3, all the way up to yk2, then to concatenate x and y together, which sometimes people will write with a dot, just to be clear, you can write this. So xy, this is actually equal to x1, x2, and so on up to xk1. And immediately after xk1 is y1, y2, all the way up to yk2. So that's what xy would look like. So if you're wondering, sometimes people will write x times y like this. Hence why I say it's like multiplying. One thing I do want to bring up, just because I talked about an idea of raising alphabets to exponents, I'm also going to talk about that idea as well when we talk about strings. So to concatenate several times a string x, say n times. So suppose I want to do it n times. We get string x to the power of n. So just as an example, just to really illustrate this, if I have x is equal to the string cat, then that means that x cubed, so this is the same as me writing out cat 3 times, right? Because I raised it to 3. So this is cat, cat, cat. So now I have an interesting question for you. And we've talked about something kind of like this just a moment ago when we talked about a set of strings. What would it be, and this is a convention more so, but it's something conceptually interesting to think about, what would be x to the power of 0 in this case? So if I give you cat and I say, oh, I have it raised to 0. Well, think about it. Think about it in terms of the number of times you're concatenating x. But namely, how many times you're writing it out. I should be a bit more precise. How many times are you writing it out? Okay, if I say 1 time, that's just cat, right? If I say 2 times, that's cat, cat. If I do it 3 times, it's cat, 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 like that. What would it mean to write out cat 0 times? What would it be then? To mean that I give you nothing. But what is that? What kind of string is that? We had a special name for this one. So what is a string that has no symbols? We had a name for this thing. Empty string. Yeah, it's the empty string. So I concatenate it no times, as in like I have the string and I write it out that many times. So this is just me writing out, say if I have x cubed like this is 3 times. I write out cat 3 times. If I write out no times, then there's no symbols, right? So just as a fun little exploration of these concepts.